Welcome everyone to the TCVS seminar for the month of May. This is the last seminar of the spring semester. We'll take a short break in summer and we'll be back with exciting seminars in fall again. So today we have Robert Kuether from Sandia National Labs, and he'll be giving a presentation on his work in as-built surface geometry effects on vibration response of jointed structures. So whenever you're ready, Robert, floor is yours.
Right. Thank you. Yeah, thank you, Professor Ajar, for the introduction and for inviting me to speak today. And yeah, and thank you everyone for being here too. I appreciate your time, either this morning or this afternoon, wherever you are. My talk is on as-built surface geometry effects, really focused on mostly vibration response of jointed structures. And so that's the theme for today's talk. Before I jump in, I'd like to acknowledge contributions from a variety of collaborators. So first off, David Nahara, he's a close collaborator of mine in the area of joint dynamics. He's at ATA Engineering. Other people that have contributed are Matt Southwick, Matt Frank, Adam Brink, and then Ben Moldenhauer, Ben Puccini, and Connor Davis from Sandia. They've provided some of the experimental measurements that I'll be showing today. So, all right, let's see. Here we go. So the topic of today is really predictions and making assessments of the vibration response of jointed structures. Joining technologies are prevalent in mechanical design, as many of you are aware. Things like bolted joints, rivets, press fits, things like that. They all rely on these mechanical interfaces that are under some sort of load, either some kind of compression load or like hoop stress load for rivets and things like that. And these interfaces introduce a lot of features. These are meant to be load-bearing features of the mechanical design. So they provide stiffness due to the frictional holding forces between the two materials under compression. And they're also known to dissipate energy. So assembled structures are known, due to frictional damping, have higher levels of damping compared to, say, like a monolithic counterpart without joints. And this is due to frictional slip at low normal contact pressure regions within the joint. And so in the presence of interfaces and joints, they really do present a fairly large challenge for the engineering mechanics community, especially in structural dynamics, in terms of predicting the response due to structures with joints, both from a modeling perspective, but also there's observed assembly to assembly variability in experimental hardware as well. So if we think about what's going on within these surfaces and interfaces, we could think about it from a tribological perspective. There's multi-physics happening, right, all at once. Oftentimes our engineering scale models don't always account for these things. Usually these are sort of homogenized in some sort of friction model like Coulomb friction. But there's a lot of things going on. There's electrical current, for example, maybe passing through and Joule heating. There's chemical effects like oxidation, corrosion. Things like wear and fretting fatigue can happen, so potentially changing the surfaces over time. And so there's a lot of happening things at different length scales. I really appreciate this image from this paper here because I think it highlights all the complexities of what can happen in these joints. And so I just wanted to highlight that to kind of motivate some of this work. But in terms of our engineering scale models, there's a lot of sources of this uncertainty that we suspect, right, for reasons why we see differences in results in test and simulation. One of those being bulk preload. We know that Using torque control methods, you can get up to 25% difference in the actual bolt preload. That's a reported value. Friction properties can change over time depending on loading history, potentially, smoothing of the surface due to wear effects. Things like surface topography, the geometry of the surface and how those surfaces are aligning with one another under assembly, that can be important. And then also residual contact tractions. As a structure, experiences loading cycles, the residual traction states can change after seeing certain types of loading. But the point of today's talk is really focusing on surface topography. What does the surface look like when it's actually manufactured and built and machined? And so we know that there's a lot of variation due to the processing, machining. And so really we can think of surfaces as probabilistic in nature. There's no real way to actually control the precise surface, at least not to my knowledge. And so we can really think of, I like to use this picture of a surface. This is a scanned image of a surface. And we can think of things on different length scales. And we've sort of broken down the sort of total surface topography into different scales. One of them is form. That's the largest wavelength scale. That's shown here. Let me see if I can, yeah. So this is the form scale. This is typically, sort of the large kind of gross, sort of non-flatness topography. Then there's waviness. You can think of this as like maybe tooling marks that you would see in a surface. And then roughness is usually what we think of, when we imagine like asperity scale. How shiny is a surface, that's usually kind of at the roughness length scale. So really it's a combination of all these length scales that contribute to the overall topography. So what should we care about? To what level do we want to capture in some of our assessments of these designs? Okay, so we're interested in surface topography, and some motivation, maybe an example of why we would care about that. One area is modular design concepts. Say we take an assembly, say part A, connected to part B at some joint, right? Maybe this is a bolted joint connecting these. Say we can characterize the dynamics well of part A individually and part B. But there's still the uncertainty that lives within the interface when we assemble these together and try to make predictions of the global dynamic response. And that's really what we care about, right? If we want to understand how an assembly, how a machine, how a whole system behaves, not just necessarily the component itself, because the dynamics are contributions of all the parts. And so if we can understand and focus on how to capture this variability and uncertainty in the interface, then that gives us a tool and a way to kind of address that both experimentally and computationally. And then we could do things like, if we understand the variation in the surface of the interface, or we can design it, then we can swap out parts. Maybe we want to attach part C instead of part B, and that's kind of the modularity concept. So we use this benchmark. It's called the C-beam. It's shown here in this image, or originally it was called the S4 beam. So maybe you've recognized that, but it's essentially this concept here, where we have two monolithic metal beams that are bolted together. There's two bolted regions, one on this side, one on the other side. And there's these machined, kind of well-defined contact areas where the interface is for the assembly. So this is the structure that actually the remaining part of it, or the remaining talk, is going to be using this to share highlights and insights that we've gained into modeling surfaces for jointed structures. Okay, so to really kind of summarize that, we want to take our C-beam We have some control over the design, right? We can choose materials, we can make decisions about finishes and flatness tolerances and things like that. So how does our as designed decisions affect our as built conditions, right? So we then have to cut metal, actually build hardware for this, and we know that we'll get some variation due to the surface finishing processes. And then once we assemble those parts, what's the variation and change in the performance of the assembly, in particular related to the vibration response. So this is kind of the goal and the topic of today's seminar. Okay, so here's an outline of the rest of the talk. So we covered background and motivation. We'll start with a first encounter, kind of our first exposure to some of these concepts, where we looked at linearized modal analysis and really tried to understand the effect of interface conditions, both for flat and non-flat surfaces on the resultant modal behavior. Next, we'll transition and talk about nonlinear modal analysis using phase resonant nonlinear mode concepts, and talk about more about the energy dissipation characterize and influence of the surface on the frictional damping in these structures using nonlinear modal techniques. And then the last topic is instead of having measured surface data, we want to actually use a model for a surface so we can then have a probabilistic modeling framework to make predictions of our performance or quantities of interest compared to having an assumed surface geometry, say a flat surface, or taking measurements and having to map it to a surface. So kind of some extensions and work we've done in terms of probabilistic modeling. And then we'll wrap up with the summary and some conclusions. Okay, so our first encounter. This is kind of how we got sucked into all this work here. So initially, we were interested in, and we sort of had some ideas, and other people have been publishing in this area too, and working in this space. And how are the contact conditions in the interface? The material in contact under preload. How does that affect the vibration response in terms of the linear modes of vibration? So you can imagine you have to linearize about some preloaded equilibrium state. That's shown here. We do simulations to emulate that, and we can figure out what material is in contact. And then we have to make a linearization step about that equilibrium state, and then we can calculate our modes of vibration. So the key quantity is really understanding how the material in contact, we usually have to make some sort of linear assumptions. Either it's stuck together, maybe it's in this slip condition where normal contact constraints are applied, but it can slide tangentially, or there's no contact. So these are the kind of tuning variables that we have for the models. So we did some projects via the NOMAD Research Institute back in 2017 and 2018, where we got some initial evidence of this sensitivity by doing experiments and modeling and simulation. So I'll go over those results. And then following the NOMAD investigations, we at Sandia then did some further work in this field and really took high resolution surface data measured from these finite element models, and then or measured from experiments and mapped it onto a very high fidelity finite element model, and then validated our predictions using linear modal analysis. Okay, so here's a summary of the results from the initial project that we did with NOMAD in 2017. So this is a picture here showing the contact pressure distributions within that mechanical interface of the C-beam. So as expected, we see high pressures, near the inner radius where the bolt goes through. And then as we move away from the bolt, we see that this dissipates to zero. And then we have regions of no contact where, the joint is prying away due to Poisson effects. So in this project, we just focused on the, nominally flat surface of this design. And we wanted to look at making some sort of decisions or tuning to capture the modes of vibration. And the things that we were tuning were what area of contact should we assume to be stuck within the bolted joint based on, informed from the preload simulations. And what area should we leave out of contact? What should we sort of not apply any constraint conditions on and leave it in a no contact state? So in this picture here, the green nodes represent, the nodes that have no pressure applied. So those are clearly not in contact. But we use this cutoff pressure value, this P sub L, to then kind of move the surface in from the interface of where it transitions to no pressure to some finite pressure inside. So this plot shown here shows the change of the natural frequency of the first 6 elastic modes of the beam as a function of the cutoff pressure. And the takeaway from this is that we can see that there's some nominal pressure value or some nominal contact area that we can tune the model to get the model to agree with the experiments. So the solid lines are the model predictions. So those are changing as a function of contact area, and you can see the sensitivity there. And then the horizontal dashed lines are the experimental measurements. So we see where those cross about the same pressure value, or at least in the same region. So that gave us a good confidence. So we wanted to, study this a bit further and really look into, well, what happens when when we account for the as machine surface geometry. So we took some measurements of the surfaces, we mapped those onto our finite element models, and then we evaluated different contact conditions for our linearized modal analysis. So this table here summarizes the natural frequency errors from the first state we considered, where the entire rectangular region is fully stuck together. This is maybe a crude assumption, but you can see there's notable errors in the frequency there. If we take our flat surface but use our preload informed contact area, we get some better results for some of the modes. But then the last case, where we actually take the surface geometry and account for that and use the material in contact for the as-built surfaces, we get a very different pressure distribution as shown here, and we get much better agreement and do a better job of minimizing the frequency error between the tests. So all this to really show that this is our kind of first insight into understanding the effect of surfaces on the vibration properties of these systems. Okay, so we took those results from those summer projects with students, and we wanted to kind of do all that again, but in a very controlled environment. We wanted to control every detail and aspect about the experiments. And so we did some investigation following that. We published a paper on it in 2020 as referenced here. But what we did was we took all the individual parts. We took the individual beams. We did modal calibration. We got the frequency errors to less than 0.7%. We used white light interferometry to measure the surfaces on each of those beams. Here's some example of data. Here's raw data. We did some smoothing with some averaging techniques, and then projection onto the finite element model. So we had high resolution data of our surfaces. And then we took mass properties of all the parts, down to the nuts, the washers, the bolts, everything. So we had everything serial, everything had a serial number, and we had very controlled measurements on all the parts going into the model. So in this way, the only uncertainty was really in the interface itself. One thing we found through this follow-on investigation, so we wanted to use pressure-sensitive film to capture what the contact area and pressure distributions are within the interface. And one finding that we discovered was that we actually needed to make a model of the pressure film in our detailed finite element models. We did some preliminary studies, with and without the film, and we found that it changed the pressure distribution as well as the material in contact. And so by the sheer fact of measuring the surface properties or the interface properties in the joint, it's actually changing the results. So if we want to compare to test, we had to model the pressure films explicitly. Okay, so here's results from our assembly model predictions. So here, this image here on the left, this is one side of the beam. And this is showing the pressure distributions, the normal contact pressure within the joint as predicted by the model with the film in it. And the image here on the right, this is our digitized pressure film from experiments. And so if you kind of compare these side by side, you can see really good sort of agreement between, these two. So we see these sort of banded structures where we sort of see three bands of high pressure regions. If we look at a different pressure range, going from low pressure to medium pressure ranges, we can see that these areas are shrinking, but they still persist in these sort of banded structures. And all of this is due to the surface geometry. If we modeled it as nominally flat, we would see that nice, regular pressure cone that we expect from contact mechanics theory. And this is the plot here on the right. This is just the other side. So just to show the variation, this is a different interface, different surface topography. And we are capturing, the surface pressures quite well between the model and the test. But they are different, from one side to the other. So it just shows the sensitivity of the surface on the static pressure under pre-compression from bolt preload. These top images here, these show, so this is not something that we could validate, but this shows the model predictions when we don't include the pressure film in the model. So this is actually what we would expect. This is our best guess at what we'd expect for metal on metal contact. And so, of course, this is very challenging to measure without putting something in the interface. Maybe you could use ultrasonic techniques, but I think it'd be hard to really get such resolution to measure this in fine detail. Okay, and then with that, we were able to then repeat our modal tests on the assemblies. So again, we compared nominally flat surfaces, the fully stuck condition. We got a mean percent error of 2% about, with flat on flat accounting for the preload contact pressures. We got down to about 1% error. And then when we account for the as-built surfaces, we got down to 0.7% error, which was on the order of the error from the individual beam tests. So we do see, again, improvement both in the contact pressure film as well as the modal results of the assembly. So the summary from our kind of first encounter was, we realized that there's this tunability of the model based on the contact area and its sensitivity to the modes of vibration. And then we've come to realize that surface topography really is a key factor, right? Surface topography changes the contact area and the pressure distributions within the joint. And we were able to validate that with pressure film measurements and comparing those measurements with high fidelity FEA simulations. And then the modal analysis results kind of further corroborated the effect on the vibration properties of the system. But we note that the linear modal analysis really doesn't account for any time varying contact conditions within the joint, because we don't expect, at low levels of vibration when doing modal testing, we don't expect much change in the joint properties. So that was kind of where we were at after the conclusion of this study. But then that kind of leads us to the next portion of the talk. Well, what about nonlinear modal analysis? We wanted to know if the surface topography was really contributing to our challenges associated with predicting energy dissipation at higher levels of excitation, right? So we wanted to use nonlinear modal analysis to capture the dynamic behavior as the joint starts to slip, as the contact conditions vary with amplitude. So we use this concept of phase resonant nonlinear modes. And so what these are, they're periodic solutions to the forced and damped dynamical system. And it's a condition in which the force and the response is 90-degree phase shifted from one another. And in this case, we're interested in the primary resonances of the structure. And so that's where this 90-degree phase shift comes from. This is also analogous to linear, resonance testing. The same extends to nonlinear resonance testing as well. And so the nice thing about these is that we can take our models, we can calculate these periodic orbits and these backbone curves and make assessments of damping, energy dissipation, as well as change in frequency. We can do this experimentally. We can measure these phase resonant curves by enforcing that phase quadrature condition in the experiments. And then we have a like quantity where we can compare, simulation results with our test results for these frictionally damped structures. And so that's the sort of the purpose and reason for choosing to use these phase resonant modes to compare between test and analysis. So regarding the experiments, so we do these so-called nonlinear force appropriation experiments. And here's a simple schematic of this test setup. So we use these modal shakers, apply some controlled harmonic force into the structure. We're able to measure that applied force and the drive point location response. These feed back to some controller, and then we can measure the vibration response on the structure with, say, accelerometers or laser Doppler vibrometry or things like that. And we use this phase lock loop controller, which basically adjusts the input frequency at a given shaker voltage. And we can adjust that frequency until we have that phase quadrature condition between, the force gauge and the measured response. And so in this way, we can isolate these modal responses at different voltage levels and back out our backbone curves from experiments. From the modeling perspective, we use the method of multi-harmonic balance. So just a quick review or intro to this. So we start with our dynamical system of equation. It has damping, it has non-conservative nonlinearities, and we have harmonically applied forces to the structure. We're seeking periodic solutions, so we assume a Fourier series for the force as well as the response. We substitute these into our governing equations, and then we do a Galerkin projection onto these onto the periodic functions, which are orthogonal to one another, the sine and cosine terms, and then we end up with this frequency domain residual equation. So this is sort of the derivation of the harmonic balance method, where our unknowns are now z, which are just the collection of the Fourier coefficients for the assumed displacements for all degrees of freedom, and then the fundamental frequency of forcing, this omega term here. So we take those equations, kind of those general derivations, and then we can add this phase resonance condition. So we can arbitrarily, apply excitation at any location on the model, and apply this phase quadrature condition at any harmonic as well. So if we look at isolating just the force at a specific location and frequency and the response, we can write a single constraint equation such that these two are, 90-degree phase lag from one another. And we can do this with this equation shown here. So we could use that, but kind of a simpler way, and maybe a more solvable way of implementing this is to just enforce that the excitation force at our input location is a sine wave, and then the response is a cosine. So we can kind of eliminate the variables by making all the cosine terms for the force 0 and the sine terms for the response 0. And then in this way, we'll always satisfy this phase condition as long as these equations are satisfied. Okay, we take those harmonic balance equations, we take the phase constraint equations, and then we combine this with numerical continuation methods. We use pseudo arc length continuation, and then we are able to then predict points along the backbone curve, and get a series of periodic solutions for the phase resonant modes of a model. So this is a nice technique. The one note is that it scales by the number of harmonics. So if you have, a fairly large size model, it scales by the number of degrees of freedom plus the number of excitation degrees of freedom. That could be 1 point. It could be all the points on the model. There's flexibility there. But then that scales by the number of harmonics in the Fourier approximation. So those models and those matrices can get pretty big. Okay, so we're going to use phase resonant modes to revisit our beam problem. Again, so this is kind of a different campaign. This was maybe 3 years later than the previous work that I mentioned. So we actually built new beams. They were made from aluminum 7075. And we looked at different surface finishes with different mean roughness values. So we did RA of 63, 16, and 2 microinch to look at the effect of finer polishing on the interface. Again, we did all of our controlled experiments, measuring mass, surface geometry, modal testing of the piece parts. We did some angled slip tests, so we tried to get an approximation of what the coefficient of friction would be. And also we used a different technique to try to get a better, or reduce the uncertainty in the amount of bolt preload by using this bolt elongation measurement, which is more accurate than the torque, the applied torque technique. Again, we did pressure sensitive film, linear modal tests, and then the results I'll talk about today are the nonlinear modes from force appropriation. So in this case, we actually used a different measurement technique to measure the surfaces. So we use this coordinate measuring machine. It's a stylus-based approach. So it can collect a grid of measurement points, position points on the surface. And this top image here shows the grid that we were able to achieve. So it had about 0.025 inch grid spacing, so very fine grid scale. And that resulted in about 3,700 measurement points along the surface. So we did get pretty reasonable surface measurements from this. This is a lot easier to do than the white light interferometry. You end up getting such high resolution data with that. And this kind of gets us, this is sort of a filter to get us sort of the larger wavelength surface features. and much less data, which is much more manageable to handle. Here's a picture just kind of showing the results of these surface scans. So on the left here, this is our roughest surface from the beams that were manufactured. You can see sort of the roughness showing up in our CMM scans. And then as you move to the right, we can see that the surfaces do become much smoother, both visually as well as in these surface scan data. What's interesting to note is even though the roughness appears to decrease, the waviness is on the same length scale between the roughest and the smoothest surface. So this kind of shows that the form error that we get out of these surfaces cannot really be eliminated due to polishing and things like that. So at least in this case, that's what we observed. And this is just visually what they look like. So you can kind of see, if you look at these surfaces, you can see tooling marks here. If you take a close look, you can see, some sort of, scratches, it appears to be on the surface. And then you see this, more polished, shiny surface on the smoothest one. So you can sort of visually confirm that as well. So we did some modeling of this. So we used reduced order models based on Hurdy-Craig-Bampton superelements. So we take our linear finite element model, create a superelement with boundary nodes defined at each of the nodes within the mechanical interface. And then we place these 3D Jenkins elements into the node-to-node pairs along the interface. So every node pair in the interface has a frictional slip element. And we're able to model the effective surface geometry by adjusting the initial gap heights of those contact elements in the joint. So before, we would have to model and modify the mesh and then run the simulations. But in this case, we're able to parameterize the surfaces on these elements itself. And in this way, we didn't have to rerun the Craig-Bampton superelement simulations every time. So this allowed some flexibility in terms of capturing the effect of the surface. So here are the results of the preload. So we had two different mesh resolutions. This is the coarser mesh here in the middle and the finer mesh on the right. And this is just showing the contact pressure distributions on one of the sides. This we classified as the shaker side versus the non-shaker side. And we see, depending on the geometry of the surface, we get quite different predictions of contact pressure distributions. And this was all for the finest, this RA value of 2. Okay, so now finally, we can look at results from our nonlinear force appropriation tests. So we ran 3 experiments on the same structure. So just kind of did some run-in tests. The first one was a run-in test. That was the black solid line. This is the change in the natural frequency, which, as you would observe, doesn't change hardly at all. And so this is not so interesting because we don't really see any evidence of nonlinearity. But if we look at the damping ratio, we do see that we are starting to get more and more energy dissipation at higher levels of vibration response. And so we start to see this kind of initial softening effect and some initial increase in damping. So it suggests to us that we're in this region of micro slip, where we haven't lost significant stiffness in the joint and gone into full macro slip, but we are starting to see the effect of slip in the joint on the damping of the system. And so we're going to focus on test 2 and test 3, because that kind of occurs after we do this initial run-in test. So we're going to add the results from the model with the flat surfaces. So this is just assuming a flat surface, not knowing any better. We can see if we look at the frequency, we get initial slipping and loss in stiffness prior to what's predicted from the test or measured in the test. If we look here at the damping, I should clarify the red curves are assuming no viscous damping. So the only damping there from the red is with friction, but the blue curves have some viscous damping informed from the low level linear modal testing. So we expect these results to agree well at low amplitudes, but we see at higher amplitudes, we're kind of over predicting the damping due to friction. Okay, and this is the result now with accounting for the surface geometry. So in observation, we clearly do better in terms of delaying the onset of slip within the joint. We get much better agreements with the test in terms of the change in the frequency. And more notably, we see much better agreement in terms of the slope behavior of the energy dissipation at higher levels, as well as the overall amplitude. And so again, the magenta is with no viscous damping, and green is with viscous damping. So the green curve, matches reasonably well with our experimental predictions, and that accounts for the uncertainty and the influence of the surface topography. Okay, let's see, how are we doing on time? Okay, maybe like 10 more minutes or so. Great. Okay, so this is the last section, and I can get through this fairly quickly, but so we had really good results and experimental validation showing us that the contact pressures are matching with our models, our linear modes are matching, and our nonlinear modes are matching as well. And all this is, when we take into account this surface effect, we kind of looked at with and without the effect of surfaces, and we can see how that changed our results. And it seems so far that it's a pretty important factor to consider, at least for these C-beams. So this kind of led us to another kind of endeavor where we wanted to account for surfaces, but we don't want to always have to measure surfaces. That, as you can imagine, is very intractable. We don't expect to be able to measure every single surface that we machine. It's costly. There's data. It'll just slow things down. But what if we can incorporate this sort of uncertainty using a probabilistic modeling framework? So let's say we have a design and we have some control over tolerances and surface finishes. We can dictate that, and then we go to have things machined. And we want to understand what are the possible surfaces that could be realized from machining, and what are the amount of uncertainty that we could see in our machined surfaces. And then if we can somehow capture that, what can we use those to make some predictions of the variability of our results? So rather than doing a deterministic prediction, say for a given surface, this is what the predicted mode frequency would be, see if we can get a distribution of results, and then make some informed decision on tying back to our design decisions like surface finish to the performance of the as assembled structure. Okay, so this is what we had done. Instead of taking measured surface data, we just used a model of a surface. And we used this Weierstrass Mandelbrot function, which is based on fractal theory. So this we took from sort of the contact mechanics tribology community as a means of measuring manufactured surfaces. And really, this model is just a function or a superposition of sine waves at different wavelengths and amplitudes, just has random phasing in between them. So any surface that you generate with a model is going to be different because of this phasing between the different sine waves. And so Here's a picture here. This top image here is a result from our function of a surface mapped onto the grid of our C-beam interface. And then we just do a side-by-side comparison with our measured surface data. And you can see that, at least qualitatively, they look in family with one another. And a key feature about the model is capturing this so-called fractal dimension, which I'll actually talk about on the next slide here. So if we take our surface scan data and we do a PSD of that, we can get this power law behavior observed in the PSD. And these green and magenta lines here, these are surface scan data. And then this black solid line is a power law fit. And so from that power law fit, we can get that fractal dimension for that function. And then we're able to match the slope of the PSD for the surfaces. So that's really the only kind of tuning variable that you would need to do if you want to generate a surface of a model, is just make sure you have the right fractal dimension. It effectively just changes the slope, where if you have a steeper slope, you'll see kind of more dominant features of the the high frequency, so high wavelength, features, versus if it was a more shallow slope, you would see a lot more noise in the surface. Okay, so our probabilistic modeling approach, similar to as follows before. We take a randomly generated surface, we map that onto our model, we make a prediction of the bolt preloads by simulating the bolt preload compression, and then we make predictions of the linearized model about the preloaded state to predict the vibration modes, and then we do predictions of the nonlinear phase resonant modes. Okay, and here's some results. Here's some results just from a single, so from the preload simulations. These curves, or these plots here, show the PDF for the percentage of nodes in contact. So you can think of this as the contact area of the interface. And this is as a function of the flatness tolerance defined on the surface. So the green curve is the sort of the largest tolerance, so it allows the most variation in the surface topography. And as we go down in flatness, we get closer to a more perfectly flat surface. And so this plot here on the left shows that when we have large tolerance and flatness, we actually get about 15% contact area compared to our perfectly flat results, which is about 50%. But as we drop that flatness down, we start to move closer to the nominal contact area. And this was for aluminum material pairings. And the plot here on the right shows a similar trend, but for steel. So you get different results because of the difference in stiffness between aluminum and steel, but nonetheless, we can show that we can actually predict distributions of results like contact area. So we can do the same thing with peak normal stress, right? So we maybe care about how much stress we're imparting on the joint. In this study here, we see that with the loosest flatness tolerance, we actually exceed the yield strength of the aluminum in this case. So you could argue that probably the results are not representative because we don't account for plasticity in these simulations, but nonetheless, it's informative to know that the effect of surface geometry on the peak stress results due to contact. But then as you make it more flat, seemingly flat, then you start to trend towards the perfectly flat results. Same thing with steel. We never exceed yield with the steel. Okay, sorry for the interruptions with the teams. I should have shut that off. And then here's results for the linearized modes. So this is just the distributions of the mode 2 natural frequencies. Same trends, as we get tighter tolerances, we converge towards perfectly flat. And then the last thing we looked at was the phase resonant modes for the aluminum and the steel beams. So we weren't able to run, I should have mentioned, we ran about 1,300 Monte Carlo simulations, just randomly sampling our surfaces. This is all that data shown in blue circles. We just took a subset of those samplings to look at the phase resonant modes. Those calculations take a bit longer, so we weren't able to afford running all 1,300 samples, but here's the results. And the black curves here, this is for the damping ratio. This shows perfectly flat results, but with variation due to bulk preload. And then the results in red are from our non-flat surface predictions, kind of picked from our samples from the previous slide. And we can see, quite a bit of variation in the damping ratio, in some of the local slopes of the damping curves. And at least it's on the, it seems to be on the order of the preload variation from a perfectly flat joint. So, so definitely something, worth considering. At least we expect to be some variation in results and explain some of the uncertainty that we see in these as assembled parts that we're testing. Okay, and same thing with the steel results. I think I'm getting low on time, so I'm gonna move on here. So so in summary, there's many sources of uncertainty that can contribute to our inability or our challenges with predicting dynamic response of both assemblies. The thing we focused on today in the talk is surface topography. And so we had some initial investigations where we looked at the effect of topography on both the contact area and the stress distribution within the interface. So we used pressure-sensitive film measurements to validate the influence of surface geometry on the preloaded state and contact pressures in the joint. And then we also use modal analysis to do vibration testing validation to understand the sensitivity of the modes of vibration due to the assumed contact area. We also use phase resonant modes, nonlinear phase resonant modes, to then evaluate the frictional damping properties. So when the contact conditions are varying with time. And again, we were able to get, fairly good agreement with our damping backbone curves on our C-beam measurements. And it was a notable improvement compared to when we just assumed a perfectly flat surface. So we know that this plays some role in capturing the right physics in these frictionally damped systems. And then lastly, we developed a framework to randomly generate surfaces. So in this way, we can sort of come up with a probabilistic modeling approach where we can use a model of a surface rather than having to take high resolution surface data. So this is my last slide before I end. And so just kind of an outlook to the future. So all this, talk about surface topography and mapping these to finite element models and needing very, some level of resolution of the geometry of the surface to capture, the friction. There's some really interesting and recent research out of the University of Stuttgart by Multi-Cracks group, where they have this coupled finite element approach with boundary element methods. So it's kind of this multi-scale approach where you can take your sort of typical, relatively coarse scale finite element model, at least relative to the surface geometry. And then you can couple it with this fine scale boundary element method. And then you can kind of couple these domains through Lagrange multipliers. And this really gives what I think is a really neat and efficient way of capturing the dynamic response of jointed structures with this surface variation. So I think it has a lot of computational speeds that they've shown and really is really kind of the key tool and technology to enable this sort of more probabilistic approach to evaluating these models. A key bottleneck is, of course, simulation time. We recognize that for sure. Okay, that's all for me. So thank you all for your attention and for being here on this Friday, and I'm happy to take any questions.
Thank you, Rob. That was an amazing presentation. Do we have any questions for our speaker? You can unmute yourself, or if for some reason you can't talk, you can drop your questions in the chat box. Yeah, nice presentation. Maybe I can start with a question for you. So the like when I think about these jointed structures and contact mechanics, one thing that always, like one question that always comes to my mind is maintaining the contact, right? So when you talk about, like the percentage of nodes that are in contact, like are they in contact all the time, or does this percentage change dynamically as the structure vibrates? Like do you take potential contact loss into account, or does that
Yeah,
make
yeah,
sense? Yeah.
yeah. No, yep, that's a great question, and yeah, it's an important detail because yeah, so in the dynamic environments, the contact conditions can change because when you're vibrating, you're loading the joint, right? It could be in a directional way. It could be shear, bending, compression. And so those loads that are imparted due to the vibration, from the vibration modes onto the joint actually change the contact pressure distributions. It can
Mm-hmm.
change contact area. These frictional contact models in finite element analysis, they capture change of contact, so it can go from in contact to out of contact or stuck to slip. So you can get those time varying contact areas and contact conditions in dynamic loadings. The stuff with like the pressure films that shows like the instantaneous, when you bolt
Mm-hmm.
together and it's just sitting there on your bench, it's not really doing anything, and that it's staying static, those contact conditions. But then yeah, of course, in dynamics, as I mentioned, it can change for sure.
Yeah, like especially determining non-near normal modes and all, like for systems that are dynamically moving, it can be extremely challenging when like take contact loss into account. It's an immensely complex problem, really.
Yeah.
Um,
And we can never measure inside, like truly measure inside the joint in dynamics. So that's all
right? I mean, there's no
out.
way, really.
Yeah. That's why we use these damping backbone curves as proxies for getting insight of what's happening in the joint.
Cool, cool. Any other questions for Rob?
I
One
got a
more.
question
Yeah,
for
go
you,
ahead,
Rob, real
please.
quick. Just out of curiosity, is there any sense of, so you've taken these surface measurements at the beginning or pre-test, um, were measurements taken post-test to kind of ascertain if these surfaces were changing throughout the course of testing?
Yeah, good point. So we have measured surfaces after. As maybe you could tell from the presentation, we kind of had different time frames of when we did some of this work. So some of the early initial work, we did do some uh, post surface scans after we did linear vibration testing, and we did observe that the surface did not change very much. It seemed to be consistent kind of pre and post test. Probably the more interesting case would have been to look at it when we did the nonlinear vibration testing because we know that we were slipping the joint and exciting the structure to higher levels. Unfortunately, we didn't collect that data and make that assessment, but that definitely would be a good idea to do if anyone was wanting to do something like this. Definitely the surface can change. You can, plastically deform the surface potentially. So, and then you can get wear effects too. So yeah, great question. And great point.
Okay, thanks, appreciate it, and great presentation.
Thank you.
Any other questions? Well, I have one final question about the probabilistic surface tool that you have. Like, how do you decide on the parameters there? Like what kind of variation you'll include in that like sort of statistically distributed surfaces. I'm just wondering, like how do you pick the variation there?
Yeah. So there was a couple sources of variation when we did that modeling.
Mm-hmm.
I maybe didn't cover it too well. I was trying to get through that part quickly, but the bolt preload. So we actually used like a plus or minus 25% of a nominal bolt preload. We just did a uniform distribution of that. Right? That's simple, but that's a source. The surfaces are so there's some limit in terms of the out of tolerance. So we were able to set a tolerance for flatness, and that kind of means like if you took a 3D scan of a surface, it has to be within this sort of tolerance range. You sort of set a limit how flat it needs to be. So, I mean, this is obviously exaggerated, but we're able to set a tolerance on that flatness and then generate random surfaces that fall in that, like within that flatness tolerance. It doesn't necessarily have to be at that flatness, but it has to fall within that range. Because that's kind of how things are, usually confirmed with manufacturing. They sort of check flatness, and
yeah.
If it's below, that's fine. If it's above, that's not acceptable. So, so the surface is generated because there's random phase variables in that function, and so every time you would say call that function, it will generate a different random surface. So that's kind of the source of the randomness.
But you still just pick it to be within the given tolerance. Okay.
Yeah. Yep. Exactly.
Great. Any final questions for our speaker? All right. With that, we thank our speaker very much for the great presentation today.